So, what we have done in the last class in fundamentals of battery pack is what does a battery pack need? We have gone to different parameters. Then we have also talked about battery pack development process. So, we have categorized battery pack into 4 categories: electrical design, thermal management, mechanical design and the battery management system. We have talked in short about all 4 domain. Then we have talked about what are the importance of these 4 categories: electrical, thermal, mechanical and BMS. Then we have talked about stages of battery pack design, where we have talked about how to configure the cells in a battery pack. We have talked in details about MP-NS theory, M parallel and N series. Then we have talked about structure, what are the things covered in the structures like case, cover, end plates, tie rods, by different definition like what would be mechanical, what would be electrical and what would be thermal parts. Then bus bar, cooling jackets, we again talked about safety, where we talked about vibration, short circuits, thermal runaway, and then control of vibration, then cell monitoring and BMS, and then application in telemetry and interface. This is what we talked about stages of battery pack design. Then we have also seen what are the major components of a battery pack. We have seen what are the major components of a battery pack, and then we talked about all the components of a battery pack like battery cells, insulation pads, base plates, side strips, end plates, cold plates, bus bar holder, bus bar, thermistor and voltage sensors, wiring harness, BMS, outer casing and all together. And this does not change. If you make a bigger pack, the number of components of each would increase. However, overall it is the same for a smaller pack or bigger packs. A slight addition depending upon the customer requirement, like do we need a vibration control signals? In that case, we can provide some accelerometer inside the battery pack that beyond a particular level of vibration, it will cut off the battery pack, like in the case of crash. Then we have started mechanical design, and then we have seen important consideration like material selection, then what would be the base plate design, how to constrain the cell movements, uniform pressure over all cell surface to improve the life cycle of the battery pack, material cost optimization, outer case design for overall protection, and then bus bar designing. And at the end, we have also talked about why packaging constraints becomes important. So, that may lead to irregular shape of the battery pack. It may not be a regular shape like a rectangular box or a cylindrical shape. It could be something, depends upon the space available in the vehicle. Then we have started the mechanical design, and then the first things in a battery packs come how to connect the cells together. And there we have talked about parallel and series configuration. A parallel configuration adds up the ampere hour current, it adds up the current. However, series combination adds up the voltage, and in a pack you may need to go on both parallel as well as series. So, generally we go parallel first and then series second. This is what we have discussed in earlier chapter, in chapter 4. Now, in building battery pack, we have also talked about how to build a battery pack. So, we have assembled the cells, a particular configuration, a particular voltage and the particular AH based upon the energy requirement of the vehicle. And we found out the pack weight is coming around 10.24 kg, and then we have started what are the force acting on a battery pack. So, it has a base plate, it has a end plates, it has side strips, it may have other components also, but right now we focused on these 3, and then there is a bus bar which is connected with the cell, which is connecting all the cells together. So, what we have talked about the major force, what is the dominant force. So, what we talked about that on side strips, it is generally a tensile force which is dominant. On the end plate, it is basically bending force which is dominant. On base plate, it is a bending force which is dominant, and the connection between cell and bus bar, it is a shear force which is dominant. And then we have started stress strain theory, where we have talked 5 different types of fundamental loading, then stress and then strain. Then we have started calculating the base plate dimension calculation. So, we know the length and the width of the base plate. However, what was not known was the thickness. Okay. So, based upon that, with giving some extra tolerance of 1 mm in base plate. So, we found that the length of base plate is 274 mm, the breadth or width of the base plate is approximately 135 mm, but thickness is not known. So, thickness is depending upon the engineering calculations, like there are some criteria, like we need to have a minimum deflection, it should be able to take the weight of the cells as well as other component. What we have done right now is the weight of cell. Then something like what we need is to minimize the cost of material. Not only the cost of material, we also want to minimize the weight. And then we will be starting from today class Ashby methodology. Okay. So, what is Ashby methodology? It is a procedure to minimize or maximize the cost, in our case, or strength or thickness. So, what are the things comes in that? What is the objective function here? Translation is first to collect all the information together. It has 4 stages, translation, screening, ranking and supporting information. So, translation, what we want and how to translate into an objective function in mathematical form, which we can solve, is basically known as translation. So, what is our basic functions here? Provide the support in base plate. If we talk about, what is the basic function here? Provide the support to the weight of cell. What we do not want? We do not want a deflection to go beyond a certain limit. That will define what deflection we want, 1 mm or 2 mm or 5 mm or 10 mm. Then what we are looking for? The cost to be minimized, and also what we are looking for? Weight to be minimized. Otherwise, we can also say thickness to be minimized, by considering that it should be able to support the weight of the cells. For now, in future when you are designing a full pack, you may have to worry about other forces also, like when there is a vibration. So, then those terminology based upon the force concept, we bring it here, but right now to make it simple, what we are considering the weight of the cells it should support. So, what is our objective basically? This is the translation, these are our wish list which we wanted to do. So, what is our objective? If I define properly, what it comes? Minimize the mass and the cost. Correct? If we are minimizing the thickness, we are minimizing the mass, and at the same time we are minimizing the cost. Why we apply this methodology? We may have several candidates, we may have a material database, we need to select some material which is of use to us, and out of those materials, that is known as screening. I may have a database of 100 materials or 500 materials, but then first what we will do after finding the objective function, what we will do, we will screen those materials. Like if there is a glass and there is a plastic, certainly we would not like to go even for glass, even if it is having too much of strength. So, we will exclude those things. Now, if there is a aluminum and there is a plastic, so we may like to go with both, which gives a better value to our things, aluminum or plastic, we may like to go. If there is a MS, mild steel, we may like to go. If there is something known as what do you say, fragile plastic, we may not like to go in that case, even though its strength is very high, but maybe in the sock, if you put a small hammer, it may crack. So, we may not like to go with that. We may not like to go with the gold. We can exclude immediately without even putting the things in the function, because its cost is very high. So, some common sense what we apply to shortlist the material, we say it is screening. So, first we have defined the function, objective function, and then now we are looking for a material database. So, what are the materials I can use? Now, after doing that, then I will put every material in this objective function, and then we will find out a material index. Now, that is a mathematically solved equation where we are finding the ranking of each of the material which we have screened already. Screening is nothing but it is a common sense what material I should use based upon experience or based upon the data available. Now, ranking is whatever material we have screened, now we are putting in the objective function and getting a value known as material index. Objective function is known as material index. Right side there is some mathematical term related to what are the things we have discussed: cost, thickness, weight, strength, all the things together. And then we find out the ranking. Now, if my function is maximized, then we will go for which has the highest ranking. If my function is minimized, I will go for lowest ranking material. Okay? And then supporting information. Supporting information is that once we have selected the material, can it work something else also? Like if I have to select, if my thermal, if I have to worry about that my heat should be transferred quickly, so I will go for a material which has a higher thermal conductivity. I can either insert in that in objective function, but in that case objective function become complex. We do not want to make the objective function too complex. So, that after screening I will see what are the secondary functions I have. If I have to release, if material index comes, ranking comes similar for two materials, then out of that two materials or three materials, if I have to select one material, then I will start looking for the secondary function. Secondary functions means in some cases we may require to transfer the heat very quick. Sometime we may not, sometime we like to retain the heat. So, let us suppose if we have selected two materials, if two materials has come of the similar ranking, one is let us suppose plastic or ABS, which we use generally for making battery packs, another one is let us suppose aluminum. If heat transfer has to be fast, what material we will select? If the ranking is similar or same, we will select aluminum in that case, because aluminum thermal conductivity is very high. If I do not want to release the heat, or I do not want environmental condition to impact my battery pack, that means I do not want outside heat to enter inside the battery pack. what we will do in that case? We will try to take a material which, if they have the similar material index, we will try to take a material which has the lowest thermal conductivity. So, in that case we will try to go for ABS. So, this supporting information also helps a lot of time to select a particular material. So, next, so we are talking about material index calculation. So, what we have discussed that we want to minimize the deflection, and the deflection is proportional to, why is my deflection? That would be proportional to Young's modulus of plasticity, and that is proportional to 1 by T cube. T is nothing but my thickness. So, if I am worrying about T, then it should be, if we want to maximize, then if we want to maximize T, or if we want to minimize T, what is our aim? Is to minimize the T. If I take T up, so 1 by E will come to minimize, 1 e to the power 1 by 3 will come, this will come. If I take T here, then this will come 1 by e to the power 1 by 3. That means, if I want to minimize T, I have to minimize 1 by e to the power T by 3. E is a constant for a particular material, but we are selecting several materials. So, E is different for several materials. So, that is why E becomes function. All other things, length is fixed, width is fixed. Again, density would change material to material, but density terms comes into mass as well as in deflection. So, we will select only one density. So, what is the function here? What we are using a function is maximize. So, if I have to maximize, what I have to do? E to the power will go at the top, because if I have to minimize, 1 by e to the power 1 by 3 will be there. If I have to maximize, just it will go in denominator. Now, it is in, so it will go in numerator. Right now, it is in denominator, minimize. If I have to maximize, it will go to numerator. The similar way, the cost, what I want to do with cost? Cost I wanted to minimize. So, if I wanted to minimize, then the cost would be directly proportional to the some numbers, whatever the cost of that one. But what is my objective function is maximize. So, it will go to denominator. So, here if I am maximizing this function, the cost is getting minimized. Similar way, what is my aim? To minimize the weight, correct. However, so if you take some function minimize weight, if I have to maximize, then 1 by weight, it will come in denominator. So, that is how this function is there. So, what we have seen? Thickness, weight and the cost, and these all the things we are maximizing. Objective function we are maximizing. So, thickness is getting minimized, cost is getting minimized, and the mass, density related to mass, it also comes into the deflection equation, but we wanted to minimize. If I have to put this as a minimum function, if I wanted to put minimize, then this would have come Cm is the cost of material rho by e to the power 1 by 3. If anything we wanted to maximize, it is directly proportional, and if we reverse inversely proportional, if we make it inversely proportional, then it becomes minimization function. So, that is what I am trying to do here. Minimize cost, minimize weight, minimize the deflection. So, now we have got two materials, ABS and aluminum. What we require is minimum information right now for selection of the material. What are the minimum information we require? Is the density, Young's modulus of that particular material, and the cost of that material. With that, we can find out the material index. Now, higher the material, since we have put maximize function, so higher the material index, we will select that material. So, which one has ABS or aluminum, which one has the higher material index? It is ABS. The ABS has the higher material index. So, that is why we are selecting ABS. Now, once we have selected the material, then for further mechanical calculations, we require other mechanical parameters, like what is maximum yield strength. For ABS, it is falling between 29.6 MPa to 48 MPa. MPa is nothing but megapascal. And then we also require Poisson's ratio. Till the time we do the material index calculation, we do not require these materials. Once we have selected the material, now we require those further properties for that particular material. Okay. This Ashby methodology is nicely put up by Ashby itself in material selection in mechanical design. If you want to have further information, you can look upon this book. Now, we have started base plate. So, what we have started? That it has to take a weight of 10.24 kg of cell weight, and then we decided let us go ahead what material we need to select for this particular. So, we have selected the material. Now, let us start with base plate calculation. So, there is a equation, Kirchhoff equation, that is a fourth order differential equation, partial differential equation. Either we can solve with the boundary condition that, or there is another way of doing that one. We use the direct formulas from design data book. One of the design data book what I have used is known as Rook's formula for stress and strain. For different boundary conditions, you get a direct formula there. If you use that formula taken from that book or any other design data book, you would be able to solve this type of problem very easily. So, maximum deflection is minus alpha q b to the power 4 e t to the power q. T is nothing but thickness, is Young's modulus of plasticity, y max is maximum deflection. Now, the second one is maximum bending stress, that is also we have to worry about, because the maximum yield strength for me is for this material is 29.6 MPa. I will take a lower range. So, what is not known? B we know, T we do not know, all other things we know. So, we also know A is the length. So, there is some terminology known as aspect ratio, maximum length by minimum length or length by breadth. With that aspect ratio, from this design data book or the formulas book, we can get the values of alpha and beta. We can get the value of alpha and beta directly. We already know the Q, Q is nothing but load. B we already know, E we already know, sigma max we already know because of the. So, what is not known? Deflection also we can constrain. I want not more than 1 mm or not more than 2 mm. My pack will support a deflection of 1 mm or 2 mm or 3 mm. So, we can select this is what I want the deflection. So, the deflection is also known. So, what is not known is T. So, from this itself alpha now we know, Q load we know, B we know, E we know, Y max also we know, deflection we know now. I have selected a value 1 mm. I do not want to go a deflection more than 1 mm. So, what is the unknown here? T. So, we will find out the T from that. So, my value of T comes approximately 5 mm if I consider 1 mm deflection. The maximum deflection of 1 mm, my thickness T comes 5 mm. Now, once my thickness T comes 5 mm, does it also solve my sigma max problem? That also we have to look upon. Sigma max should be less than, this is my design criteria for that particular material. So, this T equal to 5 mm thickness solves my both the problem. It is the maximum allowable stress also it solves, as well as it also solves my problem of maximum deflection, which I have already selected 1 mm. But sometime we may not need to go for, or we may not like to go for a thick material up to 5 mm. No. How can we reduce? Is there any way? Yes, we can do without increasing much weight and volume. In that case, what we can do? What we can do is we can provide the ribs, we can provide the stiffeners. It is like a beam you are providing. It would look like, if it is my base plate, I can provide the stiffeners like this or ribs like this for another 2 mm thick, only at that locations wherever I have put. And these numbers again based upon that, what is the thickness we wanted to go. We wanted to go for 3 mm, or we wanted to go to 2 mm, or we wanted to go for 1 mm. So, based upon that, this stiffeners, number of stiffeners you can calculate. Again the similar formula, only thing that we have to use beam theory there. So, this is how we have calculated everything for the base plate, the maximum bending stress and the maximum deflection. This was 2 parameters for us, and which we have solved. We got a particular thickness, and we do not want, if we do not want that particular, if we did not like that thickness, that no, this thickness is too much for my pack. We also found that how can we reduce the thickness further by providing ribs and stiffeners. Again we need to calculate by similar theory how many ribs or how many stiffeners we require, what would be thickness, what would be height of those ribs, all those things we can calculate, the similar formulation. Now, the second thing what we have talked about in the battery pack design is the end plate. Why end plate become necessary? Why end plate design becomes necessary? Because it provides a constant pressure on the cell surface. Why the constant pressure is required on the cell surface is because of the life of the cell. Otherwise, what will happen if you do not provide sufficient pressure on that cell surface, the cell will bulge, it will require more volume. The life cycle of the cell will come drastically down, which you can see from this curve, that if I do not provide any pressure on the cell surface, if I do not provide any pressure on the cell surface, a cell which is supposed to go for 2000 cycles approximately will work only for 100 or 150 cycles. So, it is important to provide some pressure, some uniform pressure on the cell surfaces. What would be the pressure? Generally it comes from the cell manufacturer, that if you provide this much, this is the optimum pressure, this is the optimum pressure range for the shell. And then once we know from the manufacturer this much pressure we need to provide on that cell surface, accordingly we design the end plate. Again, to provide the pressure on the cell surface, what will happen? There would be a reaction force on the end plate. You see here, if pressure will go there, then there would be a reaction force on the end plate. What this reaction force will do? It is a uniformly distributed force. What it will do? It will again try to bend the end plate. So, for this one particular cell, what we found out that around 14 psi pressure would be a optimum pressure for the cell life to go up to 2000 cycles. The conversion factor is given. 1 psi is 6894.676 Pascal. Now, sometimes you may not get the information from the supplier or cell manufacturer. What you will do in that case? You have to do simple long time experiment. You keep on charging and discharging, put 2 plates, put the pressure sensors, keep on changing the pressure, and you see what is the life cycle of that cell. So, it is a tedious and long time process, very simple, but tedious and long time experimental process. So, it is always good to get the information from the supplier, or if we are using the same cell for different, and we have a roadmap for next 5 years, we will be using the same cell. In that case, we can also re-verify all those information given by the supplier. Now, I am not going to solve this in-plate support problem. I am going to give you an assignment on that. The battery pack what we have designed, on the same battery pack, end plates and side strips are required to be designed. Material selected for this purpose is aluminum. Base plate we have selected as a ABS, but let us suppose we have selected aluminum for this end plate as well as side strips. We know the length, we also know the pressure value. Please find out the thickness of the end plate, because again length and the width is we already know. What we do not know is the thickness. Now, for the side strip, this side strip would be holding this end plate for that particular pressure. So, there would be a tensile force on the side strip. So, what we wanted to know, what would be the cross sectional area of side strip, because force would be acting on that. Since we are not giving you width, so we want the cross sectional area. The boundary condition 3 is fixed, length and width you know, one free end. Use the same formula book which already we have given here for alpha and beta formulas here, and solve this problem. It is an assignment question.